Hello, welcome to one more lecture, and now we are seeing applications of quantum mechanics in engineering in general, especially in biomedical engineering. The last lecture I ended by explaining to you the electron tunneling microscopy. This is a wonderful device that by keeping the tunneling, which is a quantum effect at the surface, we can map everything. We can actually see steps on the size of one atom. We can see missing atoms. We can see molecules that are deposited on the surface. We can see everything. And I explained to you how is the mechanism that works, and it's based on the relation that we deduce that guarantees that keeping the space, somehow we keep the tunneling flux, the tunneling current. So, but the electron microscope is not the only example of tunneling. Reactions in biosystem is another one. And let's see some of these examples today, which are applications, right? So we're going to see some reactions that depending on the tunneling effect, which is a full quantum mechanic effect. In biological system, most part of the time, there are barriers. And we know that electron transfer, proton transfer, ion transfer, all this kind of thing is very important on the metabolism going on in the biological system. And they find those barriers, and sometimes those barriers just stop the running of the metabolism, the occurrence of the metabolism. And in those cases, many tunneling effect helps the things to take their natural course and go on. So normally when we have those biosystems, energy may or may not be available for many of the reactions that will take place. Right, and this is a nice picture that we see two types of making the reactions to go on. One is that this is like, you know, normally we can represent this in many things, but normally you have the system in one kind of potential energy, and you have to move to the other one, which is not in the same place of space. And that can happen in two different ways. Either you give energy to this particle, and then normally we call this thermal activation, and you all know that thermal activation is a very important thing on bioreactions. And normally what's happening is you give enough energy, and particles get this energy and are able to go through the barrier, go above the barrier, coming to the other side where things is happen. That sometimes happens, and this is very important. And we have many different types of reaction that happens that way. But there is an important one, which is the tunneling. You know, tunneling is a different things. Particles will not get thermal energy and overcome the barrier. They will pass through the forbidden region, and then quantum tunneling may take place. So I believe that in many aspects we have thermal activation all the time in different metabolic reactions, but we have also quantum tunneling in many different reactions. And the quantum tunneling is very important in many situations. I'm going to give you some examples here that is related to quantum tunneling. Those are different molecules. I'm not going to try to speak about their names because they are complicated. And we're going to, you know, there are different chemical reactions that calcigenate this type of thing. And normally it has to go from one stage to the other one. Those are different states. I'm going to highlight. You know, you put this in calcium hydroxide, and you calcigenate this molecule. This happens all the time. So we have this state. This is a molecular state, which can be represented as being one energy level, one energy state. To come from here to the next state, that is a big necessity of energy to move things around. You see how many things we move around, how many electrons we move around? So to come from stage 1 to stage 2, that is a big energetic barrier. And it turns out that at the moment in the system, you do not have that energy. So this modification, which is fundamental for the continuation of some metabolic reaction, calcigenation happens all the time, everywhere. So for this to take place, for this to come from here to here, you must either go above the barrier, so you have to get enough energy to move those bounds around, or tunnel to this barrier. With less energy, you may be able to tunnel. And you may guess at this stage what the system goes through. It goes through a tunneling. So this is a metabolic reaction of calcigenation and has to come to a stable configuration of the calcium and the hydrogen and everything. So this split of the bound and the reconnection, everything here, must be done. And there is no energy in the system for that. So it's complete equivalent to particles tunneling to barrier, because they are in one stage of energy. They have a potential that holds them there. So here, it's like having a potential that holds the system here. But this is not what the system has to do. It has to go to other configuration of lower energy, more stable. But to do this, it has to overcome a barrier, because the intermediate things of this demands a lot of energy. And the system does not have that energy. So it tunnels to this barrier. So there are many chemical reactions happens in your body and any living object that goes to this. And guess what? If you go to the biochemistry good books, you find that they define it very well. This is normally, they have different or coordinate for this, but doesn't matter. What's important is you have a product here. And you're going to have to move things around to go to another stage. And you have to somehow go through the barrier. Guess what is the barrier penetration integral? Which means, what is the chance for this to come? Is this theta of energy, which is basically everything we have done. You know, here they define a little different. Biochemistry define, they don't put the 2m divided by h bar square and everything. They really define a little bit, but it's the same integral. It's the same integral that characterizes the tunneling effect. And the tuning probability is also calculated the same way and depends on the exponential of this. Right? And then they normally comes to a tunneling rate, which is basically what I calculate before. I did that for the decay of the alpha decay of the nuclei and everything. So the difference of energy here, dW, is the barrier width, because you have the potential. You come from this point to this point. So you going here, they call W the coordinate, right? It's okay. V of W is fine. So this is the width, because they call W because of width. And they have, the system has to tunnel to some distance W, delta W. And then the barrier height, which is this, is basically the energy of the things, the maximum of the potential minus the energy, because the energy is here. The energy of the particle will end here. This is the energy that the particle will come out. So we define this, and we can write everything in terms of this. reduced mass, speed of light. That's a different way of putting things. Turning points, reactive frequency. That's exactly the frequency that we found in the... and Planck's constant that comes in a different way. So all the bio definition of this reaction to tunneling is basically what we deduce in the barrier, right? And that's here. And that's determine the rate in which reactions in the metabolic happens. And there are many of them taking place in your body and many other living objects. I would like to end this example by saying that quantum tunneling is essential to understand the chemical reactivity in metabolism. Essential. And when you do biomedical engineering or any other engineering that's related to life, we must know reactivity. We must evaluate reactions. We must do that. And quantum effect, especially the tunneling, is there. And you get to understand the main principles involved to be able to understand what you're measuring. Okay? Quantum tunneling is the wave nature of those particles that make them occupy, make them pass through barriers that they could not pass classically. It's like light passing through glass, right? This is exactly what's happened for the matter wave when they tunnel too many things. Okay, here I found in a book a very interesting definition, and I wrote it here, reproduced here because it's interesting. Tunneling requirement. Tunneling is highly dependent upon to the mass of the particle, as we saw, and the width of the barrier, as we saw, and now you know how that depends. The barrier could be a physical distance. The less massive the particle and the narrower the barrier, the greater likelihood that tunneling will occur. This means that light particles such as electrons and hydrogen atoms, and in rarer cases heavier atoms, may influence the reaction and reaction rates through tunneling in reagents are held in close enough proximity. When reagents are held in close enough. So basically, you know, it's fully admitted that the importance of the tunneling in this process. I got one example that, you know, when you speak about bio stuff, you cannot forget about the most important reaction we have, which is the respiratory chain of mitochondria. So here, if you take the respiratory chain of mitochondria, biochemistry made a wonderful work in finding out how things are converted. And you know, the respiratory converts, it's the big production of ATP, right? So it's essential for us. ATP is produced in the respiratory chain of mitochondria. And then there is a big chain of electrons and protons transfer. In many cases, I don't know how much you can see, but those are pathways of electrons. And in all of those, they have barriers that they have to overcome. All those are electron pathways. And of course, you have a lot of transport of protons. Those are electron pathways, and they have a lot of barriers to bypass, to overcome, and they have a lot of protons transfer. Believe me, there are here a lot of tunneling going on in different steps. We're going to get, in the later applications in your course, some of those individual steps to try to do a model and to do some calculation. But in many, many, many different steps of the respiratory chain of mitochondria, there are electron transfer. And some of them, there are tunneling effect. And there are tunneling effect also by the charge, by the protons, which is the lightest particle that's still an atom that we can have. So if tunneling is important there, remember the mass is important. For the proton, tunneling happens in many different situations. And finally, when you have this hydrophobic gate, that's what they call, is when things can pass to where it should not. So you have molecules, and they come to places where you have this hydrophobic barrier. You know, hydrophobic is avoiding some water, right? And then it turns out that some ions which should not be there, they can come and pass through. So this is tunneling of potassium ions in those hydrophobic gates or barriers that happens in the metabolism. And before I finish this part, you know, there are also evidences of tunneling in the synaptic electron transference. And you know that the synapse is this connection. You have all the bio stuff involved in here, mitochondria and everything. And you have a flux of electrons that must pass through. You have calcium ions that may transfer, may help. And then you may have tunneling. Electron quantum tunneling is an important effect on the synaptic electron transfer. And this is a very interesting application, right? It's you know, everything concerning with neurons and stuff, we're still learning a lot. And the evidences that may have electron quantum tunneling here is really impressive and make us to think that there are a lot of quantum effects going on in our brains and in other parts of our neural system, which are tremendously important, because the electron to migrate from one neuron to the other, it must also tunnel. This is what this paper was showing to us. And finally, in the olfact, they claim that for molecules to reposition themselves so they can be detected by our olfactory system. This they call olfactory receptors. They claim that there is tunneling going on for the electrons from the donor to the acceptor. And this is something that they tested with many animals, and I don't know how they test everything, but it seems that even our ability to smell things has quantum effects involved, which seems to be impressive. I think all these things of tunneling, quantum effects in quantum, and quantum in general in bio is a ongoing field, and I'm giving just like informative effects, right, that people are discovering that makes the quantum tunnel effect that we just saw to be very important. Okay, well, then enough for the tunnel effect, for the applications. And before the end of this lecture, I really would like to explain to you a little bit more fundamental now, so we can, I give you all this quantum tunneling and everything. I spoke about flux and everything, but I have to give you some more basic information now, because you know this is fundamental. You have to get to those fundamentals, so all the applications became easier. Okay, so I want to tell you a little bit, changing gears here. You know, we did the tunneling, we did the applications. Now I want to go back to this probability conservation, or the flux probability, or the density probability that we are using all the time to characterize the particles in your quantum system. We learned from the very beginning of the interpretation of the wave function that the density of probability actually is the wave function squared, the modulus of the wave function squared. And this modulus of the wave function squared can be stationary, but can change in time. When it's changing time, means that the density of probability is not being conserved. So if it is not conserved, somebody is either giving or taking density probability for the system. So this is what I'm going to cover now in this part of the lecture, is this quantum conservation of probability. And the way I want to do this is by what we call continuity equation. Continuity equation, we learn continuity equation in many fluid mechanics. We learn everywhere that you have something that overall has to be preserved, right? Then either it's kept there, or if it varies, that quantity is going somewhere. So if we have a density of probability or density of many other things, and it is varying in time, and this is represented by the time derivative, it means that you have a flux. So something is going out or going in. If this is increased, it's because this is going in. If this is decreasing, it's because this is going out. The divergence of a flux give you how much is going in or out. And that's why we call this the continuity equation. And it's valid in many things, right? It's not only here. Fluid mechanics is filled with this, and fluid mechanics is very important for biomedical. So this is the continuity equation we have. And that means that if you have a place everywhere in some space, sometimes it's the real space, sometimes momentum space, sometimes it's everywhere. And we have a region with some density. Here, density of probability. The variation of this density is either due to the flux coming in or flux coming out. And we wanted to understand this on the context of probability density, which means the wave function square. But the first thing to do is, what is this flux of probability? We learn what's the density of probability. Now we have to learn what is the flux of probability. And I'm going to consider only the Schrödinger equation. And I'm going to consider free particles, because it's simple. If I have a free particles, the equation, the full Schrödinger equation, not only the time independent, the full time independent, is given by this I h bar d dt of psi is minus h bar squared divided by 2m. This time is the second derivative of psi with respect to the space. We learned this equation. We solved this in a few situations up to now. And of course, this is a wave. Most of the time it's complex amplitude, because oscillatory and oscillatory stuff are represented by complex. And we have the I in here, which is also complex. Now I'm going to take the complex conjugated of this equation. So take the complex conjugate, I becomes minus I, and whatever you have, t and x are not complex. We know the spatial coordinate and the time coordinate, but the psi is complex conjugated now. Right? So up to now is very simple. This is true for a free particle. Now I'm going to start with the density probability, which is the product of the two, the wave function and the complex conjugate, which give me the modulus square. This is the density, and I explained to you arguments before why we consider that as density. And everybody agrees, and everybody was happy. I'm going to start with this, but I have to keep in mind those two relations, okay? Cannot forget those two relations. And what I'm going to do now is basically take the density and make the derivative of the density. Time derivative. Well, I have the density as the product of psi star psi. It's a product of two functions. When I take the time derivative, I use here the chain relation, and I take the derivative of the first times the second, plus this first times the derivative of the second. Right? Right. So the derivative of the density of probability is this derivative, is these things. But I learned a few minutes ago how is the time derivative. If I take this expression, I know what is the time derivative of psi and psi star. So in the place of psi star derivative with time and psi derivatives with time, I'm going to replace it by those quantities here that I just calculate directly from the Schrödinger equation. So I'm going to replace this guy by this. You have to put a term in here because there is IH bar there. But then the time derivative became the second spatial derivative. And in the place of this guy, I'm putting this guy here. So this is what I have at the end of the substitution, which is simple. Right? And then you see, this is like taking the derivative of a product again. Because I have a derivative of this times this, and you have the derivative of this times the derivative of that. Actually, if you look careful, this is exactly the spatial derivative of this quantity here. Because this will be the derivative of this times this, minus the derivative of this times this. This will cancel something, and then we will end by having the second derivative in there. You could see that, right? It's simple. So all this can be put in that way. So, you know, by the help with the Schrödinger equation, I convert the time derivative of the density of probability in the spatial derivative of a quantity. But if you remember, the time derivative of the by continuity equation, if probability is preserved, which we believe it is, this should be equal to the time derivative from that equation. The time derivative of the density should be minus, here I put divergence because it can be general in 3 dimensions, but if it is in 1 dimension, it's just the x derivative of the flux. If I pass to the other side, this should be minus equal to minus the spatial derivative of what I'm going to call flux of probability. And just by looking here, you can identify the expression for the probability flux or flux of probability. And who is this flux of probability? Is this nice quantity. When I have a particles represented by a wave function, the flux of probability is h bar divided by 2im times the complex conjugate times the time derivative of psi minus the times the spatial derivative minus the spatial derivative of psi star times psi. This is actually the flux. So if you keep that quantity in mind, which is the flux of probability, because we didn't know the flux of probability before, we construct that for a 1D system. If it is not 1D, this has to be replaced by divergence, right? But for 1D, the continuity equation demands that the time derivative of probability is related to the flux of probability. This is interesting because this already is somehow making strong our interpretation of probability for psi square. And this is somehow important because if probability density varies with time, and we're going to see many examples now and after when we put the time-dependent potential, like light and everything to excite molecules, it must exist a flux going somewhere. Now that we know everything about probability in quantum mechanics, I'm going to go back to that case of particles flying around, you know, free particles that can be going or coming back. This is the part that's going, this is the part that's coming back. And I'm going to calculate, and this is the wave function. For this, remember, the particles that comes to the barrier had a 1 exponential of ikx, and I told you this is the incident, and exponential of minus ikx, which is the returning. If I take this wave function and I calculate the flux, well, bingo, the flux of probability is this quantity, which is basically velocity. This is the momentum divided by mass, is velocity, times the density, which, as we know from any fluid mechanics, flux is equal to density times velocity. Just to remind you that, right? Here, when we do that, we just plug in the expression. It's very easy. We get that the flux, depending on the difference of the amplitudes of the incoming wave and the outgoing wave from some region, which tell us that the net flux depends with what's coming in and what's going out. If A is equal to B, this is 0. And the density in that region of space will not change at all. Now, if A square is bigger than B square, means that there is a net flux positive, which means more particles are coming this way than going back, because this part represents the particle going that way. If A square minus B square is the density of probability, and then this is the net velocity, and this is what I told you before, that all flux in physics is always a kind of velocity. In this case, the velocity of the particle, the classical velocity, times the density. And here the density is the density of probability. But remember, we saw the tunneling, nice tunneling to a barrier. We create a barrier, we send a flux coming, and then if you go back now and find what is the flux in this region, it has the incoming flux, because it's 1 minus r squared, if you just calculate. Which means the overall flux in this region is whatever is coming in to the barrier minus what's reflected by the barrier. And what is the flux going out there? Well, the flux is going out there is basically this proportionality constant times t squared. So t squared actually is the density of probability. R squared is density of probability. And here the density of probability is 1, because it's for sure this guy is coming. Now, if you have a physical system where the wave function is real, like inside the barrier, when we saw the tunneling effect, inside the barrier, we found a real wave function. What's happened when we have a real wave function? Well, if we have a real wave function, the complex conjugated and the function itself is equal. So this gives you 0. So if you have a real wave function, the flux is 0. There is no flux probability in that region, right? So nothing is really flowing there because the flux is 0. There are density, but they are constant. There is no flux. So actually, when I have the barrier and I measure the flux, that's 0 here. It is existent in this side of the barrier. It is existent in this side of the barrier. So actually there is a current coming in if it is electron, current coming out, but the flux inside the barrier, which is the forbidding part, is 0. The particle actually comes here and jumps to here. It's like, right? There is no real particle being accumulated there, even though there is probability. But there is no flux. Now, because whatever is in this side, nothing is being accumulated here, has to be equal to whatever is in this side. So 1 minus r squared has to be equal to t squared, which gives to us, by this flux interpretation, that r squared plus t squared is equal to 1, which we used before because we knew the probability has to be conserved. And now we did by flux, which is really interesting and important in this case. Fine. Well, that will be happy to finish the lecture today, but I want to show you an example that is like an infinite size barrier. So we're going to do an example that is go and calculate, but now will be much simpler because we know everything about the wave functions. So we see the probability when there are a step variation. Well, by the way, we see a lot of probability flux variation in time when we have a transition of electrons from one state to the other, from one configuration to the other, and we're going to go back to this. Now I want to consider an infinite barrier. So this is a barrier that you see is 0 here, and that has a step function. And then I have an energy that's less than, of course, the step. So for the case where I have less than the size of the step, we all know the incident is this. Right? We know that. We already learned that. But because we are telling that there is a flux coming into this step, we're going to have the coefficient here as 1. So actually the wave function in the first part, which is before reaching this step, is e to the ikx plus r, because there is a chance of reflection, of e to the minus ikx. And in the second part, which is inside the barrier, we already solved something similar. We're going to put minus h bar squared to m, the second derivative, is equal to plus v0 psi is equal to e psi. We take the e this side, and we call beta square, and the other part we call q, but now we're going to call beta, and we get this equation. And we know, because you are good students, whatever I have the second derivative minus a constant, real constant, times the function, the solution is exponential. I can have a positive exponential or a negative exponential. If I consider the positive exponential, means the wave function will grow when I grow x, and blow up in the infinite. So this is no good solution for this physical system. This is no good. I kept only the negative. That's the only one that obey the fact that the wave function must die to 0 in the plus infinite, because the particle cannot survive there. So the second function is like this, and the picture we have for this is just the oscillatory wave here, and a spontaneous decay when we get inside the step. Now, if we calculate the region 1, we get this. If we calculate the step of the region 2, we get that. The flux here is the combination of the two, and the flux on the other is 0. Very good. Well, you can consider also, and that is the other interesting fact. So the density is preserved in time. Whatever the flux is 0, right? Another problem is the step, but the energy now is higher than the step, above the step. And in this case, we have for region 1 oscillatory behavior, and we have for region 2 another oscillatory behavior, but with different K. While the first momentum is just depending on the energy, the second one is just depending on the available energy, which is the energy minus V0. So all this is left here can be the momentum, can be the kinetic energy, right? So we have this as the momentum on the second. So this is a problem that I have two momentums to deal with. And when I solve the problem by inputting the boundary conditions, which is the wave function has to be continuous, which give me the relation between A, B, and C, which are the coefficients of the solutions that we have here, A, B, and C. So by inputting the equality of them in 0, we get the relation between A, B, and C. And then when we input the derivative, we have also the relation. And then we can get the rate between the C and the A, which is basically the probability of transmission, which is this square, and B over A, which is the probability of reflection. And then we can get the flux, the incident flux, or the flux on one side, which is the incident flux minus the reflected, and the transmitted flux. And it just put in a picture way, you have here particles with momentum 1 propagating in two directions with a net flux, and then you have the transmission on the barrier, which is, this is really not tunneling, this is just the transmission to a barrier. So this will be like actually the wave, the light in passing through a transparent material. You know, you're going to decrease the amplitude, but it's going to continue to propagate, and this is propagating with a smaller momentum. That's why the oscillation reducing space. Here was oscillating faster because the momentum is bigger, the wavelength is smaller. So this wavelength is bigger than this because momentum changed and went down because of the step that took part of the energy as potential now. We can calculate the transmission coefficient for a step, and it is the ratio between the momentum here squared divided by the sum of the momentum in both sides. You can see that if I make the barrier goes to 0, K2 will be equal to K1, and in this case this gives you 4, this gives you 1. So if I kill the step, all the wave will pass through, the transmission will be 1. Okay, so we learn a lot about transmission. By the way, this step is not tunneling. When I gave the step, the energy bigger than the step, it's not tunneling, it's just the transmission of the wave, okay? And when I gave the energy less, the penetration in the barrier is a frustrate transmission because there is no flux. To really recapture the flux, I will have to cut. If I take this and I have this step, and then suddenly I come here and I cut this here, then I catch this little part of the frustrate transmission, and that will become a flux again. But if I keep this infinite, this will die out and there will be no net flux in that region. Good. Okay, so today we learn many things about application of tunneling in biosystem, and we learn about this conservation of density of probability and flux of probability. The introduction of flux of probability is very important. Why is important? Because in many cases, you'll be facing the situation to really calculate the flux, right? And calculating the flux is something that's very important. And if I have a 3D system, the flux is still preserved. We just come with a vectorial here, and this part is replaced by gradient. Gradient, okay? If we want to generalize it to a 3D system, we do that. If that comes to some applications that we're going to do, we can just remind you about and generalize and everything. So you see that our course is evolving a lot. We are now in a situation that we can quantify all this quantum phenomena. And next lecture, we're going to continue with this by localizing particles. We have to understand localized particles because that's the main nature of chemical bound and by the interaction of light with matter and everything. So we got to do that. Okay, thank you very much. See you next lecture.